Okay, welcome back, everybody. So we have a very short lecture today. I'm not going to say too much more about certification, but I have notes on my website with a bunch of links to articles if you're interested in exploring this area more. So as far as like widely available and widely used software, there's two big ones. The first one is Alpha Certified for proving that approximate solutions are indeed approximate zeros in the technical sense to a polynomial system, meaning that they are in the basin of quadratic convergence of Newton's method. This is all based on Smale's alpha theory, and it's a fairly conservative condition to be shown to be an approximate zero via Smale's alpha theory, and that means it's expensive, but it does work, and you can prove that you have approximate zeros, and that if you have two approximate zeros, you can prove that the associated true zeros are distinct, if they are indeed distinct. And then interval arithmetic allows you to bound the image of interval boxes under polynomial maps, and in particular bound the image of interval boxes under the operation of Newton's method. And if you show that this is a contraction, then a fixed point theorem tells you that you have a unique fixed point of Newton's method in that interval. And since the fixed points of Newton's method are just the roots, you prove that you have unique roots in these intervals. And then of course it is simple to show that two interval boxes are disjunct. So these are really the two main things you can do. You can certify some notion of having an approximate solution, and you can certify disjunctness, that you have distinct approximate solutions. And this means you can certify lower bounds for the number of isolated regular solutions to a square polynomial system. So it's very importantly square in these methods. And then if you have theoretical upper bounds, either from Bezout or BKK, then paired with the parameter continuation theorem, you get honest to goodness proofs that you have found all of the solutions. And indeed, you can also certify reality here. So you can certify when these approximate solutions correspond to real solutions. So on my website, I have some links. So let me just pull it up on my end here of some more recent trends in the certification world. Yeah. So there's a few papers linked. Handling overdetermined systems. Overdetermined systems really will show up in your life if you continue to work with polynomial systems. And out of the box, you shouldn't be trying to certify anything about them because these methods only work for square systems, and squaring it up might cause issues. And so there's a whole slew of papers about, well, what can you do when you have an overdetermined system? A really exciting avenue, which I'm really looking forward to having an implementation in Julia for this, is the ability to certify homotopy continuation effectively. So whenever you use the word certify, there's this big question of like, what the heck do you mean, right? So even if I say like certify that I had an approximate zero, you have to choose what you mean, and these are two distinct meanings of what that could mean. So what do I mean by certifying homotopy continuation? I mean, if you have homotopy continuation, then you have some start solutions, and you have some target solutions. And so these live over some t value, call this t equals 1. lives in some solidity n. Now I can box any of these and do like interval arithmetic and certify that there's a unique solution in this box, right? So the analog of doing that along the process of homotopy continuation would be to essentially bound this whole path by a tube. So that these tubes don't intersect. And that would certify that no path crossing could possibly have happened. Okay. And so what do you earn from that? You earn a proof of the bijection you get from the start solutions to the target solutions. Right. So it's one thing to run homotopy continuation because you really want these targets. You can run homotopy continuation, get your targets, certify your targets, and you would be certifying something. You would be certifying that you bounded, the isolated target solutions. But along the way of that process, you may have had a mutual path jumping or something like that. So you may have had, so for example, that goes there, that goes there. You may have had a jump where both paths swap. Okay. Now you don't care about that if all you care about is finding the target solutions. So what if they found some other funny, incorrect way of getting to the correct answer at the end? I really don't care. I can just after the fact certify my target solutions. But a lot of times you're not just interested in knowing what the target solutions are, but you are actually interested in this bijection. And so the major instance where this is the case is when you're computing monodrome. Okay, so if this path corresponds to some loop, so at t equals 1, it's the exact same solution set as t equals 0, then having a certified homotopy continuation method like this allows one to prove that a certain permutation belongs to the monodrome. Okay. And that allows you to prove that certain groups are subgroups of the true monodrome. So this gives you one direction of certification of monodrome groups. There's the issue of certifying roots with multiplicity. So people have studied this, so certifying isolated singular points and their multiplicity structure. There's more interesting stuff about certification of real structure of solution sets. Yeah, so there's a bunch of links in the notes on the website. And so feel free to explore those, shoot me an email if you have any questions about them. Maybe I can answer. Okay. Any questions about certification and what I've mentioned so far? Okay, as far as future directions go in numerical algebraic geometry for certification, I don't think there's a catch-all method for handling overdetermined systems. As far as I know, the methods in the literature all require some extra information that you have to know about your system. So that'd be good. But the most important one, in my mind, like really the holy grail of certification in numerical algebraic geometry would be to certify the trace test. So this interval arithmetic method, the alpha theory method, they both give you ways to certify lower bounds for the number of isolated regular solutions to a square polynomial system, but they don't give you upper bounds. Right? They don't tell you that you found all the solutions. You could get an upper bound from theory like Brysiewicz or BKK, But the question here is, could you ever get an upper bound strictly from numerical computation, some sort of certification method? And that's not clear to me. The first place to try to do that would be in the context of witness sets. Because in the context of witness sets, we have a verification method for verifying that we found all the solutions, right? So we take the trace and do some parallel slices and show that the trace moves linearly. But that's a verification method. That's not a certification method. And it's really, really important to know the difference. So verification methods, if they pass, you bet your life savings on the result, and it's fine. You trust that the answer is true, but it's still not a proof. Certification gives a proof. Very, very interested in ideas on how to do this. Okay, so I'm going to pause the recording and we're going to jump over to the computer for a moment, and I'm just going to show the basic functionality of certification in homotopy continuation, and we'll just kind of explore what kind of object gets returned to us and what kind of fields that object has, etc. Okay, so great, so I'm going to share my screen here. Here we are. Can somebody confirm that they can see this?
Yeah, we can see.
Yes.
Thank you so much. Great. So I've copied in the code that we've really been using since the beginning of the semester here for finding the 27 lines on a cubic surface. So great, here we go. So we have 3 variables for the cubic, lots of coefficients for a cubic. Here we build the cubic up in this nested loop. We write down some coordinates for a parametrized line, parameterized by the variable t. We make some assumptions about this line without loss of generality in the generic case. Parameterize the line correctly. There it is. We evaluate the cubic along the line and ask that all the coefficients of this cubic in t are 0. And we take those coefficients, there are 4 of them, because it is a univariate cubic in t. And we write those 4 coefficients as the 4 equations of a polynomial system whose parameters are the coefficients of a cubic and whose solution variables are the variables describing the parametrized line, the u and the v. It's not too ugly, but let's not look at it for too long. And we can solve it any way we'd like. Here we did a monodromy solve. So I think I can pull the parameters. Yes, there's the parameters that we've solved over. And then there's the solutions. There's 27 of them. Hip, hip, hooray. Okay. And so homotopy continuation is super user-friendly. I think I might get in trouble here. We'll see if this works. So this is what I'm going to try. I'm expecting that I might get an error here because I don't know if it plays nicely with parameterized polynomial systems or if I have to actually evaluate the polynomial system at the parameters. Nope, it plays nice. Hooray. Good. Okay, so what is returned is a certification result. And it gives you 3 numbers. The first number is how many points you gave the function certified. We gave it 27 points. The second is how many interval boxes surrounding those. So for each one of those points, you take an interval box, like itty bitty interval box containing that point. And you ask whether or not this cross-check operator, which is a wiggling of the Newton operator, is a contraction map. And if it is, then it gets counted for this second number. And then finally, it checks how many of those interval boxes are guaranteed to be distinct. Okay. So for example, so let's take a look at what's inside. So we could look at what the certificates even look like. So I think I can ask for the first one. And so this is some object in Julia, some structure, and its fields seem to be a solution candidate, is certified, a certified solution interval, precision, is real, and index. So here's the candidate. Here's your interval. So remember, we're in 4 variables. And each variable is a complex number. And so it needs a bounding box. To bound the real part of a complex number, you need 2 floating point numbers, or just two numbers. And to bound the imaginary part, you need 2 numbers. So each coordinate needs 4 numbers. And so that's what we see. So here, they represent it as like the center of the box plus or minus some like radius of the interval, right? So the real part is within 2.74 e to the negative 14 of 0.530425, blah, 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 blah. So that's the real part of the first coordinate. Here's the imaginary part of the first coordinate. And then indeed, we have that for every coordinate. Okay. All right, and we can check the next one, and we get the same thing. So maybe we can do S real equals solve F S start parameters equal P target parameters equals ran float 6420. So the difference here is so before when I did monodromy solve, it chooses a complex parameter. And now I'm going to take those 27 solutions and I'm going to use them as a start system to solve for a real parameter. How many? 64 parameters according to this. So we over approximated. Oh, and you know what? I actually want that parameter too. So P real equals, because I'll have to plug that into the certification software anyway. 64. S real will be solving over P real. Okay, cool. So now we got some reality information, and so we can ask to certify F at S real P real. Great, and it's giving me these results. So that's not real, that's not real, that's not real. So many are not real. Let's see, which one is gonna be real? Is real. There we go. 21. There we go. So that one's real. Okay. Good. So this is a proof. C is a proof that there are 27 isolated solutions to this polynomial system over these parameters, 3 of which are real, 24 of which are not real. There could be more. But what this certification result says is that there do exist 27. 3 are definitely real. 24 are definitely not real. So let's see what happens when we give it like bad information. Yeah. So I am going to make that's bad. I'm going to add some duplicates in here. Length of a span. Uh-oh. There we go. So now I'm going to give the certification software 30 solutions. And yeah, so if it tells me that there are 30 certified distinct solutions, you can ignore everything I've said this week. Let's see what we get. Right. That works. Yeah. That's interesting. Sorry, just gotta get it into the right type here. There we go. So I gave it 30 candidates. And indeed, all of them are definitely associated to some true isolated solution. So if I take a box around any of these sufficiently small, I can, it proves that it's a contraction map. But that doesn't mean they're distinct yet. If you ask how many are distinct, it says there's 27 distinct ones. 3 are real, 24 are complex. Okay. All right, any questions about how to interpret the output here? Okay. Oh, great. Now you can start proving theorems using numerical algebraic geometry. I'm going to pause the recording and we'll take a break before the final lecture of the course.